bit of dark and large, a little history of this large-scale structure. So this will be from the CMB, what we just heard about, up to present day. So here is Henry.
All right, hello. Thanks for having me here. So, yeah, I'm going to talk mostly about the logical structure and about what's going on. So here's the basic problem that I'm going to talk about. We think the universe is made of mostly of these three components. There's dark energy, about 72%, dark matter, about 24%, and this normal matter, that's, we are like a tiny fraction of that. And we think this is roughly what the universe is made of. The problem is, we don't really know what dark energy is, and we don't really know what dark matter is. And I'm going to talk mostly about dark matter, because dark matter is important is very important to generate the structure of the universe and where the matter is. And notice that, they wrote normal here, but because we're only a tiny fraction of it, we're the exotic ones. So what is dark matter? Yeah, we have no real idea. Or we have many ideas, we don't know if any of them are correct. And so, why do we think it is there? Let's see about that first. So, back in the 1930s, there was this friendly guy, Fritz Zwicky, Swiss astronomer in California, and he observed clusters of galaxies and was looking at how do the galaxies move in the cluster. And he found that these galaxies, they're moving too fast. The cluster should have dispersed and just flown apart a long time ago. And so he proposed that maybe there's something called dark matter that we cannot see. But okay, this guy, you believe him? So forward in the 1960s, there was a grad student, Vera Rubin, who studied not the whole cluster of galaxies, but just single galaxies and how fast they rotate. And what she found is that so she studied how they rotate, and she wanted to match, does that match how fast they do rotate? And you would think that if you go further out from a galaxy, that the rotational velocity would just slow down, because you're far away from the object, it should go down. But what you found is that no, the stars, they continue to rotate very fast around the center of the galaxy. And how does that happen? There must be something here that we do not see. And so, people didn't really believe Fritz Zwicky that well. She really made it clear that dark matter is something we need to worry about, and we should really understand what is going on. And then in the years since then, some different kinds of evidence for the existence of dark matter came about. For instance, there's like a cluster where you don't just use optical light, but X-ray light. And I'm not going to go into the details, but you can see that most of the mass is where we don't see anything. Similarly here, we have clusters of galaxies, and like in the foreground there's a cluster of galaxies, and in the background you have a background galaxy that gets lensed. And so the light from the gravity, from the mass, gets bent around and creates these weird arches and structures like that. And in order to explain this, you actually need dark matter. And so this is a real picture out in the sky, and it kind of looks nice, doesn't it? Yeah, so no photoshopping there. So dark matter, why don't we see it? Well, there are four basic ways that we could detect something. Because there are four forces of nature. And there's gravity. We've known about gravity for a very long time. And it shows here, the picture just shows Newton's apple falling to the ground. And dark matter clearly interacts gravitationally. Then there's electromagnetism. Electromagnetism is a very important force. It is responsible for light, it is responsible for chemistry, and dark matter does not participate in this interaction. So we cannot see it via light, we cannot see it via any kind of chemical processes. then there's the weak interaction and the strong interaction. And the weak interaction is a very weak force, and the strong interaction is a very strong force, because physicists are creative in that way. And let's start with the strong interaction. The strong interaction is what holds, like in an atom, the nuclei together. And we know that, well, since it's a strong force, we would probably see it if dark matter were to interact with it, so it doesn't interact with the strong force. So our best hope, besides gravity, which is how we discovered it, is the weak interaction. And we don't actually know if it interacts weakly or not. But this is what people try to use. And the weak interaction is a very strange force. It is how a lot of nuclear power works, and it can do a lot. But it's weak, and so it's hard to detect. Doesn't matter. Okay, there's lots of dark matter around there, and dark matter is very important because without it, we wouldn't have large-scale structure in the universe. We wouldn't have, probably wouldn't have galaxies, or only very few of them. And so we need it. So here's a small history of the universe. Professor Sarah Chandera just showed something very similar, where we start at the beginning with some kind of inflationary period, and then we have the CMB over here, which has small fluctuations, and then we go from these fluctuations over time, structure grows, and we are over here now observing, say, the CMB and everything in between. And so what I'm going to talk about is mostly how dark matter is responsible for much of the structure that forms here. And so if we look back in time, we have here the CMB, we have a dark period where not many stars were formed, then the first stars form, and finally galaxies form. The Earth forms around here, like 4.5 billion years ago, and we are over here. Okay. So the end result of this is how do we see galaxies clustered in the universe? And in this picture, you can see, let's say the Earth is here at the center, and you go out in distance here, so it's called redshift here, but it's really distance. And then if you just take a slice of the sky, you can see that all the galaxies that we observe, every dot here is a galaxy, they are distributed like this here. And you see like clusters of galaxies, and they're connected by filaments. And you can see also voids where there are very few galaxies. So our universe basically looks like, kind of like a bubble foam, kind of like the foam of a beer, where you have these clusters of galaxies and voids and filaments. So to create this, you need dark matter, and the way people found this out is by running simulations, like on a gigantic supercomputer. And so let me show you this, the Millennium simulation, which was finished in 2005. And with here they simulated a very large part of the universe and just let it run. So every point here is a dark matter particle. So what you see here is not galaxies, it's dark matter, because dark matter is really the important part that makes this all happen. And just see it zooming in here into a simulated cluster. And like there's a supercluster and smaller clusters around it, and the filaments and the voids. And so dark matter, this is the dark matter, but of course the normal matter, us, preferentially clusters goes where the dark matter is. It gets gravitationally attracted, and so that's where galaxies and stars form. Okay. All right. So it just keeps zooming into this cluster, and we can continue as long as we want. Okay, there we go. I think that's all I want to show. There's another simulation they created a simulation. So that was just today. The same group made another simulation where they started a bit earlier in the dark ages, and here you can just see it rotating and the dark matter collapsing and just forming structure and galaxies and stars and planets and whatnot. So yeah, this just kind of continues here.
What's the number in the upper left?
So the number in the upper left is the redshift, and it basically tells us is the time when this formed. But so here's the time in the right and on the left. And what is happening is that if you have a universe that is expanding, the light needs to somehow get towards us first, and as it travels towards us, the light gets stretched, and Z is exactly that number that tells us how much that light got stretched. It's called the redshift. So here you can see that all the other galaxies and the filaments from the outside, they start falling into these centers of where most of the dark matter is. Yeah?
Is that like a single, like an elliptical galaxy in the middle, or single galaxy?
Yeah, I think that in this case, it's a gigantic elliptical galaxy in the center. I think so. Okay. Okay, so let's move on. So I think now most of the cluster has formed, and it just continues growing slowly. Let's let it go. So we'll be here done pretty soon. Okay, let's continue. So some of you may not like equations, and so I'm not going to show you an equation. I'm going to show you an unequation, and it's very important that dark matter is not equal to dark energy, because some people get that confused. But they have some commonalities, and the most important one is that we don't know what either of them is. Dark matter, we know a little bit more about dark matter. It has mass, and it slows down the expansion of the universe because it has mass. And it is very important for structure formation. That's why we exist. Dark energy, on the other hand, speeds up the expansion of the universe, and that's all we know about it. Okay, so here's my summary, and I think I'll just leave it up here for you to see. So, if there are any questions?
Anyone have a question?
So, when normal matter collapses, it can use its electromagnetic interaction to just pour off energy so that it can, condense.
Mm-hmm.
But since dark matter interacts so weakly, is it possible for it to condense, or would it always just pass right by itself?
Right, good question. So the question is, normal matter somehow gets rid of energy so that it can collapse further. Whereas dark matter, it doesn't really interact that much, so how can it collapse? Wouldn't it just keep being hot and being puffed up? So the important thing about dark matter is there are different variants, and there's hot dark matter and there's cold dark matter. And so you need dark matter to have a certain property so that it is cold. If it was hot, then you would have exactly the problem that you're describing, that it wouldn't really be able to collapse. And so the paradigm that we have now is that it must be cold dark matter for that exactly to happen. So it already starts out slow.
Is dark force what
or dark energy what drove the original inflation of the universe, or is that entirely different?
That is entirely different. It could have a similar mechanism behind it. Oh, all right. So the question is, dark energy. Is dark energy the same thing that created the inflation at the beginning of the universe? Right? So it could be that there's a similar mechanism, but generally it's quite different, because that happened early on in the universe, and this is now a very late time acceleration, and they probably have very different origins.
Anyone else? Yeah, back to your comment about the four basic forces.
Mhm.
Yeah, there. The strong interaction is an extremely short-range force.
As long as right,
How
right.
would you tell whether or not it's involved in dark matter?
Right, so actually, maybe I should make it a little... Oh yeah, so the question is, the strong interaction is a very short-range force. It only interacts on very short scales, like atomic scales and subatomic, nuclear scales. How do we know that it doesn't react like this? So actually, there is a possibility that it does, but if it did, like there's probably dark matter in this room right now, and if it did react strongly, we would probably see some kind of strong interaction with it in the lab. So that's why it probably does not interact strongly.
But you'd be looking at small scales.
Right. So, but there's a lot of dark matter. So.
Anyone else? All right, I've got one more question. So, the hot topic, of course, is aliens. Could aliens be made out of dark matter, and can we tell?
Well, we can't tell today, but so there's speculation that there's an entirely alternative dark universe behind ours that could potentially be richer than ours. Maybe they know about us.
Okay.
But yeah, it's an open speculation question.
So it's a possibility.
Yeah, sure.
All right, thank you again.